Hey everybody. This will be a quick video on some of the properties of logarithms, and then we'll do two quick examples of how to use some of these properties to solve some exponential or logarithmic equations. So the first two properties pretty much fall out straight from the definition of a logarithm. So for any base b, log base b of 1 is 0. Why? Well, remember the definition of logarithm says that in this expression this is equivalent to saying b raised to the 0th power is 1. And yeah, any number except for maybe 0, any number raised to the 0th power is 1. So log base b, whatever b is, log base b of 1 is always 0. And you can check this one yourself using this exact same method of just rewriting it in its exponential form, but log base b of b for any number b, any applicable number b, is 1. Let's see here. Two properties called the inverse properties basically state that logs and exponential bases raised to exponents, they kind of undo each other as long as they have a common base. So log base b of b to the x is just x. So log base b and this base b, you can think of them as sort of canceling each other out to just leave x. Similarly, b raised to the log base b of x is also just x, assuming that x is greater than 0. So again, b raised to the log base b, it's almost like they just cancel each other out. They're kind of like inverses. The log function is injective, or one-to-one, as they call it, which means that, I didn't even finish writing it out, that if you have log base b of m is equal to log base b of n, this is true if and only if m equals n. So when you have two logs, the same base, and they're sort of written out this way, you can just sort of cancel. You can think of the logs as canceling out. So log base b of m equals log base b of n means that m equals n. That's required. Let's see, the maybe three most important ones, most useful ones that tend to come up in solving these sorts of problems are the product rule, the quotient rule, and the power rule. So the product rule says that log base b of m times n, so when there's a product inside the argument, you can really split that up as the sum of the log of each of those pieces of the product. So log base b of m times n is equal to log base b of m plus log base b of n. So if they're being multiplied inside of the argument, you can break them up as log base, the first piece, plus log base, the second piece. Quotient rule is the exact same thing, just with quotients, and as you'd expect, rather than splitting up as a sum, it splits up as a difference. So log base b of m over n is equal to log base b of m minus log base b of n. And then finally, my favorite rule is called the power rule, which says that log base b of m raised to the nth power is equal to n times the log base b of m. So it's kind of like this n, the power, can be pulled down in front as a coefficient. So log base b of m to the nth power is equal to n times log base b of m. All right, well, let's see if we can put a couple of these together to solve some problems. So the first one is an exponential expression. It says 3 raised to the quantity 11x plus 4 equals 17. So in general, when it comes to solving expressions that have the variable mixed up inside of the exponent, the very first thing that you need to do is take a log of both sides. And you'll want to choose your base of log strategically. You can use any base technically, but at the very end you're going to have to start plugging things into your calculator. So it's smart to either use log base 10 or log base e. I prefer log base 10. A lot of places and textbooks prefer the natural log base e. I don't really know why. Doesn't make any difference either way. Maybe it's just fewer things to write. So in any case, my first step here, since I have x wrapped up inside of the exponent, I'm going to take the log of both sides. So log, and remember, if there's no base specified, it's implied that it's base 10. So log of 3 to the 11x plus 4 equals the log of 17. So I'm just taking the log of both sides. That's fine. This is legal to do because of the injectivity of the log function. So this is kind of like me going the reverse way from m equals n over to log base b of m equals log base b of n. So just taking the log of both sides. Well, now that I've done that, I get to use my favorite rule, the power rule, because inside of this argument on the left side is this power, 11x plus 4. And you need to pull the full power down. So, and I'm going to put it in parentheses, 11x plus 4 times the log of, all that's left in there is 3, is equal to log of 17. So that step right there was the power rule. And now we just go through and we solve for x as usual. So first thing that I'll do is I'll divide both sides by log of 3. I think that sometimes feels funny for people because log is a function, but log of 3 is just some number. So it's the same as if this didn't say log of 3, but if it was like a 9 or something, you would just divide it over. It's the same thing here. So I'll divide both sides by log of 3. 11x plus 4 equals log of 17 over log of 3. And then just solve for x. So it's going to be subtracting 4, dividing by 11. So x is going to be log of 17 over log of 3 minus 4. All of that over 11. Yeah, it's a really weird way of writing that. That's the precise answer. Let's see what it comes out to. So, log of 17 divided by log of 3. And here's how I do it. I'll show you how I do something like this where it's kind of nasty. Rather than doing it all in one big swoop, I'll do it pieces at a time. So first log 17 divided by log of 3 gives me some answer. And then rather than writing down that answer, I just kind of like chain these together. So now that it's given me that answer, I'm just going to hit the minus button. And see how it autofills? Answer minus, it means whatever the last answer was. So I'm going to subtract from that 4. Gives me some new answer, and then the very last thing is to divide by 11. So about negative 0.1292. Is what that comes out to. And you could, of course, just plug this back in. You could plug negative 0.1292 into this for x and solve all of this out. Since I rounded it, it's going to come out a little bit different, but it should be pretty close to 17, like right in the ballpark of 17. All right, here's another one, another question or problem that's maybe a little bit trickier because it's going to result in an extraneous solution. So, all right, well, let's see. How do we go about this? So first of all, we're trying to solve where does log of x minus 3 plus log of x plus 1 equal 1? Well, I can use the product rule in reverse to rewrite this left-hand side as a single log. Right? So right now I have the sum of two logs. I can rewrite that as a product. So I can rewrite this as the left-hand side becomes log of x minus 3 times x plus 1 equals 1. I don't need to do anything on the right-hand side yet. I've just manipulated the left-hand side. All right, well, now what do I do? Because now I have this variable x is wrapped up inside of the log argument. Well, I can use one of the inverse properties to get rid of the log on the left-hand side. And in particular, the inverse property that I want to use is this one right here. B raised to the log base b of x equals x. And the way that I do this is I will raise both sides as exponents with base of 10. So the base here is 10, right? So like this one is saying that if I have b raised to log base b, they kind of cancel each other out. So if I have 10 raised to log base 10, they'll cancel each other out. But if I do it to the left side, I've got to do it to the right side. So basically what I'm saying is, we'll say, well, this is equivalent to 10 raised to the log of x minus 3 times x plus 1 is equal to 10 raised to the first power. And now I use the inverse property to say that, well, this left-hand side, the 10 and the log just cancel each other out to leave me whatever is inside on the argument. So x minus 3 times x plus 1 equals, and then on the right-hand side, we can just calculate that out. This one's nice and easy. It's just 10. But if it was some other nasty number, if it was like 1.7, then it'd be 10 to the 1.7. Just put that into your calculator, and that's what goes on the right-hand side. So now we're at something that you're probably really familiar with solving at this point. This is going to end up being a quadratic. So we need to FOIL out the left-hand side and solve this thing. Let's see. So the left-hand side is going to become x squared minus 3x plus x, so minus 2x minus 3 equals 10. So x squared minus 2x minus 13 equals 0. And I need a little bit more room. All right, that's not going to factor, right? There's no way that that's going to factor cleanly, so we'll use the quadratic formula. Let's see, I'll keep it kind of consistent here. So x is equal to, I just got to plug things into the quadratic formula. X is equal to 2 plus or minus the square root of 2 squared, so 4 minus 4 times 1 times negative 13 all over 2. Let's see here. Rather than taking up much time on the video, I have my notes here. Yeah, so this should end up being 2 plus or minus the square root of 56 over 2. Square root of 56, you could simplify that. Yeah, should we actually? Let's see, 56, what is 56 is 8 times 7, is that right? So 4 times, why is this so hard for me? 4 times 14, is that right? Yeah, 8 times 7 is the same as, 4 times 14. So it would be 2 plus or minus 2 root 14 over 2, or 1 plus or minus root 14. So you've got to be careful here, though, because this is saying that there are two different solutions, one plus square root of 14 and one minus square root of 14. Just really quickly, 1 plus the square root of 14, well, square root of 14 is larger than 3. It's between 3 and 4. So this is something that is positive. Great, yeah, fine. The trick though, is that 1 minus the square root of 14 is negative. And the domain of the log function is all the positive numbers, everything greater than 0. Which means that anything that is less than or equal to 0 is not in the domain. And the original function was, or the original equation was given as just like the left-hand side is logarithms. So this number right here is less than 0, and in particular, this is going to be less than negative 1. Well, I guess actually I can even stop right here, right? Because if this is negative, 1 minus square root of 14 is negative, then subtracting 3 from that is, again, even more negative. So plugging this in to this first piece, log of x minus 3, it's a domain error. So it's out of the domain. So this is an extraneous solution. So the only solution is 1 plus the square root of 14. So you got to be careful because the step where I introduced some issues, the extraneous solution was this step right here, when I raised everything to the 10th power or as base 10 in order to cancel out the logs. That's where I introduced this extraneous solution right here, because this is a quadratic that has two solutions. This one, though, it could potentially have two solutions, but it turns out that one of the solutions that is yielded by this quadratic is extraneous. So you need to make sure when you get to the very end, especially if you have two different solutions like this, you need to make sure that both of them are good. In this case, the only solution is 1 plus root 14. All right, there's that. Let me know if you have any questions.